Okay, so good evening, dear colleagues. My name is Nikola Cvetanovic, and I will be chairing this session, this unusual poster session. So hopefully everything will go okay. It is a new thing for all of us. So I will first explain the procedure. I'm sure we will do our best, both the organizers and the participants, to exchange ideas and to make this poster session as normal as possible. First of all, I will call the authors of the three authors that have applied for the short 3-minute presentation of their posters. And after they're finished, we will call out poster by poster to see if there are any questions from the audience, and the authors will respond. While they respond to the questions, we will show their posters on the screen. So first would be the poster number 6 for the short presentation.
Yes.
Are you here?
Yes, I'm here.
Sorry, how is your surname pronounced? Alat, right? Yes?
Saad.
Okay. So you will be presenting the analytical formula for the output factor calculation of small radiation beams, yes?
Yes, right.
Okay, so if you can start, you can share your screen.
Yes,
or
please.
should.
Yes, please.
Or should. Okay.
So, can I start sharing?
Oh, maybe I should share the screen. I'm not sure what was the. Yes, you will now be given rights to share your screen. And just wait a moment. Can you see the share button? It's the third button.
Yes. I found it. Just easily. I don't know, where is it? It's not my screen. I can't recognize I can't recognize my mail. Start Firefox. Maybe I don't know.
Okay, it's starting to share now.
Yeah, 1 minute. Okay, that's it, right?
Thank you.
Okay, let's start. Analytical formula. First of all, hi everybody. I'm Saad from Hungary. Analytical formula. I would like to present my posters about analytical formalism for the output factor calculation of a small radiation beam. And I would like to define the output factor, or what I mean by output factor. The output factor is one of the most significant factors that used in radiation dosimetry and medical physics, which are affected by different factors, like the size of detectors, gas field detectors, the size and the type of collimators, and also the medium density. And the main or the aim of this study is to find the corrected output factor for different collimator size, starting from 10 by 10 down to 1 by 1 centimeter square, and also different collimator types such as multi-leaf collimator and jaw. And also to find the analytical formula to calculate the corrected output factor without any further measurement. As you see here in this picture, you can see the gantry or the head of medical linear accelerator, which represent the radiation source, and this represents the experiment setup. And we have here the water phantom, which represent the medium of measurement where the detector, gas field detector, exists. and the distance between the source and the surface of water, we call it the surface to the source to the surface distance, which is important and fixed during measurement. And finally, we figure out, or we found the analytical formula to calculate our output factor. As you see here in the middle of a poster, you can see output factor equals to the output factor at the zero field size plus to the corrected output factor at a certain field size. And another formula represents the deviation, standard deviation. And you can see over here the output factor. I just want to change the view. Okay, here, over here, you can see the output factor measurement at 6 mega electron volt for photon beam for different ion chambers, starting from the smallest one, pinpoint ion chamber, down to the largest one, Farmer ion chamber. In the first graph, you can see here in the y-axis, output factor. In the z-axis, you can see the field size, and we have two measurement. We have in the green line the output factor for the jaw, and you can see the deviation for output factor at small field size. And in the red line, we have the output factor reading for the MLC in the red line, and the solid black line represent the fitting line or our corrected output factor. The second graph represents also the output factor that measured by semi-flex ion chamber, and you can see also the output factor measurement become worse because the size of detector increase. By the way, the size of pinpoint ion chamber, it's about 0.01 centimeter cube. The semi-flex size is about 0.125, and the output factor becomes worst at small field size than pinpoint ion chamber. And the last figure represents the output factor that measured by Farmer ion chamber. Validation, experiment validation. The analytical formula for output factor was verified and compared with measured data for both MLC and Joe Shep's PM. And as you see, we have validation for three ion chamber, pinpoint, semiflex, and Farmer. And we recognize the difference in our measurement for the small field, the smallest field size, roughly at 2 by 2 and 1 by 1 centimeter field size. And we realized that the difference in our measurement between calculated measurement or calculated output factor and measured output factor was very large between Joe and analytical formula, and it was very small between MLC and calculated one, because we have some radiation leakage from MLC that contribute to the point of measurement and rise the measurement up. And also we saw the same for semiflex ion chamber, and also the same for Farmer Wellhofer ion chamber. In conclusion, we found our formula is good and give a good agreement with the measured data, and we recommended to use this formula to calculate the output factor without any further measurement for a specific type of medical linear accelerator like ELICTA, and also we recommended to use it for commission data or for routine to use routine by routine QA quality assurance for radiation dosimetry in case of absence very small detectors such as pinpoints, micro diamond, or even diode detectors. And that's it. Thank you for attention.
Okay, Saad, thank you very much. So thank you for this presentation. It was like a short talk almost, very nice. So
yeah, thank you. Thank you.
Do we have, so I will just ask the audience now, do we have any questions?
Mm-hmm.
I don't see Any questions?
No questions.
No
Okay.
questions. Okay.
Okay.
So thank you very much again, Said. We will go on now to the poster number 14.
Mhm.
So I think it's Majkic. It's Milena, I think, yes?
Yes, we had her at some point, but we lost her from the session.
She was just here a moment ago. I saw it.
Yes, yes, but she's disconnected now. Okay, I see her.
Okay, she's again too. Here, okay. So the title is, it's a long title, Ionic Velocity as a measure of an interplay of the neutralization energy and the deposited kinetic energy in the surface. It is from the section 2. The first one was from the first section.
Yes.
Are you here?
Milena, do you
Milena,
hear
yes?
us?
Yes, I'm here, but I can't share my content.
You can try.
You have
Maybe
all
I can share.
privileges? She's presenter, she should do it. I mean, she could do it.
Yes, yes, she should.
Milena, can we help you?
I don't know. I tried last week. It
Shared content
was
button.
okay, but I put share content, but
Is your poster open in some window on your computer?
yes. No.
So when you push the share content, what's happening? Do you have windows that you can choose from that you want to share?
It's starting.
I can't see my poster. Maybe later.
You can just click on your PDF.
Yes, I have PDF. I don't know.
There it is.
Do you hear? Do you see?
Yes, we see everything. It's nice.
Sorry, I'm sorry. Okay, the role of this, the title you read is title, and the poster is about the role of the ionic velocity in the nanostructure creation during the interaction of highly charged ions with solid surface. In that purpose, we consider highly charged ions, xenon ions, approaching perpendicularly the metal surface at low to very low to moderate ionic velocity. And during the ionic motion, cascade neutralization of the ions occurs, which means the population of highly Rydberg states occurs through a barrier between the ion and the solid surface. During the cascade neutralization, during the neutralization of the ion, neutralization process, during the neutralization process, the neutralization energy released and deposition into the surface, which leads to a surface modification. We use two-state vector model and micro staircase model for the analyze these two processes. Within these models, we define relevant physical quantities such as flux, transition probability, population probability, and the main quantities are the final ionic charge, which describes the state of the ion in front of the solid surface and neutralization energy. Neutralization energy we defined with this relation. The first term represents the ionic potential energy before the neutralization process, and the second one represents the ionic potential energy after neutralization process. We consider arbitrary ionic velocity because for very low ionic velocity, the neutralization process is almost complete and neutralization energy is equal to the potential energy. For moderate ionic velocity, the neutralization process is incomplete, and for the surface modification, we should take into account except both neutralization energy and the positive kinetic energy. Because of that, we define the critical ionic velocity for which these two contributions are equal. For velocities lower than critical ionic velocity, the main contribution in the nanostructure creation gives the neutralization energy, and for velocities larger than critical velocity, required energy consists both of the neutralization energy and the positive kinetic energy. These are valid for metal vacuum system, and this also can use for the analysis of the neutralization process in the metal dielectric vacuum system. For this, we consider the nanocrater formation by the impact of highly charged xenon ions on metal surface covered with thin dielectric film. During the cascade neutralization and through the electric and also surface modification, the electric is strongly perturbed, and because of that, instead of the initial ionic charge, we use the effective ionic charge. In this figure, we present the neutralization energy and the positive kinetic energy for this process. We consider the charges from initial charges from 25 to 45, and because of perturbation of the dielectric, we have effective ionic charges. These quantities are presented in the table, and we present also the critical ionic velocities. We denote these quantities by symbols, and these quantities we obtain as intersection of these curves. The critical ionic velocities are in the region of the velocities used in the experiment, which means for the nanocrater formation, required energy consists both of the neutralization energy and the positive kinetic energy. Also, for the critical ionic velocities can be used to predict the particular form of the surface nanostructures for a given ionic velocity. That's all. Thank you.
Are there any questions? Oh, sorry. For your lecture. I will now ask the audience if they have any questions. I don't see in the chat anything. Are there any questions in the chat? I didn't hear.
I think no questions so far.
Okay, so I'm not an expert in this field, but I would like to ask Milena a simple question about the from the technical point. How do you do this calculations of equations? Do you use some specific software or for the numerical calculations, or it is mostly analytical when you solve these equations?
We use the analytical methods for these equations.
So you directly obtain the formulas. So thank you very much again. If there are no questions, we are going now to the poster 15.
Yes. Hello.
It's 15. Yes, it's Ziya Iman, I think. Yes, you wrote to us today. Yes.
Yes, Iman Ziyayan. Do you hear me? Okay.
Yes.
Now
You
share.
come from Hungary, yes, and there is a state selective charge exchange cross-section poster in B4 plus.
Yeah.
So it is a collision of heavy particles.
Yeah.
Okay.
Do you see the poster now?
Yes, we see you're doing great. Yes, we can see the poster. Yes.
Okay.
You can start.
Hello, everybody. Thanks for giving me this opportunity. The title of my work is a state selective charge exchange cross-section in beryllium ions and ground state hydrogen collision system. In this kind of collision, the hydrogen's electron is transferred to the beryllium as a target. In this regard, we use the three-body classical trajectory Monte Carlo method, as well as quasi-classical trajectory Monte Carlo method of Kirschbaums and Violets. The cross-sections were obtained when the target's electron is transferred to projectile quantum numbers equal to 3s, 3p, and 3d. So, as you know, the beryllium is considered as the armor material for plasma-facing components of fusion devices, and it is the first wall of the ether. So, the inelastic collision process between beryllium ions and hydrogen are particularly important. The quasi-classical trajectory Monte Carlo is one step further for a better description of the classical atomic collisions. As you know, for atoms, a necessary condition for stability is that the electrons are not allowed to collapse to the nucleus. And this condition motivated by the Heisenberg uncertainty principle. So we used one quantum concept into the classical simulations. The theory of calculations based on the Hamiltonian of the system. So we put the extra term as Heisenberg potential into our calculation to see the results. Okay, as you see here, the figures for 3s and 3p and 3d states of the projectile show that the results based on Heisenberg potential, as you see here with the blue line, are in the excellent agreement with the quantum previous results. So as you see here, the quantum previous result based on the molecular orbital close coupling, the atomic orbital close coupling, one electron, the atomic molecular, and boundary corrected continuous intermediate states. So according to figures, we found improvement in the cross-section using the quasi-classical trajectory Monte Carlo method compared to the standard classical trajectory Monte Carlo method. That's all. Thank you for your attention.
Thank you, Iman. It was a very concise and concrete lecture. So are there any questions in the chat? I don't see any. Are there any raised hands? Please feel free to incorporate in this discussion. This whole session was meant by the organizers to be more like an exchange of ideas, but I think that due to this online method, you are very shy mostly. So please feel free to raise your hands or just write a question in the chat. This is can I ask some questions then, of course?
Yes, of course.
So you are calculating the cross sections of heavy particles of beryllium 4 plus and H, and as you said, it could be applied in the tokamaks. Yes, if I understood correctly. So the beryllium would be then like a spattered material within the gas and then collides with H. Yes, or
yes, yeah.
So you're calculating the spattered beryllium,
Yes.
and
yeah.
And it occurs like a charge exchange collision, as I can see. Yes, you are making. You're changing that.
Yeah.
Okay, so it's very interesting. Yeah, I think it's very applicable. Can you obtain maybe some? For me, it would be interesting if you can obtain some differential cross sections or only total. Is it possible to?
Yeah. All of these channels are possible. The ionization, the total cross section, the differential cross section, and the state selective cross section. All of these channels are important and are practical, and we can find all of these channels into our simulations.
That is very interesting for me. For instance, when you're doing some simulations of plasma, Monte Carlo PIC simulations, it's very interesting.
Okay, thank you.
So thank you very much for your lecture. If there are no questions, we have finished our first part of our poster session. So I would like now to ask all other attendees, since we have time, feel free if you want. You can now choose to present your poster in a way that you saw now, for instance, from Iman, a few minutes of presentation. It would be very nice. So you can change your time. You can change your mind whenever you want within this poster session. I will call out now poster by poster. So you can raise your hand if you want to present your presentation now. For instance, now when I'm asking, or when I call out your poster, somewhere in between, anywhere you can just report or write to the chat. It would be the easiest. You can see the chat on the right side of your screen. You can just write, I would like to give a short presentation. And it seems more practical than just looking at the poster and asking questions. So please, I would like to encourage you, feel free to give a short lecture. You can just show your poster like your colleagues did. So is there anyone that please raise your hand or write to the chat that you would like to give you a lecture? Let's ask again. Okay, we have Dr. Chades raising hand. Would you like to give your presentation now? Can we move him to the panelist? Okay, can you hear me? It seems that his microphone is.
I cannot unmute him.
Maybe he muted himself. I don't know if that's possible. So, Dr. Chades, can you hear us? Can you start your click on the unmute button, the first button on the left, with the image, with the picture of microphone, icon of microphone? So, host, why do you think this happens? What's the problem?
I don't know. I cannot unmute him completely. He has a presenter's role and he's a panelist, but I cannot unmute him.
Oh, maybe you can share the screen and open his presentation, and he can go back as an attendee and then get the microphone off.
Dragan, are you here? I can also hear parts of your sentences.
Do you hear me now?
So, okay, so maybe we should continue then.
Do you hear me? I hear you.
I see here parts of his.
Fine. So we have your audio. If you have problem sharing, I can open your poster and you can talk. Maybe that's easier. How? I don't know if you are having problems with your connection.
Do you hear me? Do you hear me?
Yes, now we do. Yes.
It's collapsing. So
okay.
you
I
can
will open it then.
Somebody else.
Okay, I will.
Okay.
It's the number. Which number was it?
It's 8.
8, yes. Okay, so I will just open it and then you can talk. Okay. So you can just tell me when to move to the next slide because you have several.
Okay.
This is the title. Resonant electron scattering by metastable nitrogen. Revisited.
That's it.
Okay, we are listening.
Okay. I don't see it, but I will put mine, which I have here. Okay, now. Okay, you can skip to the second one. It's just done.
Okay, we are on the second introduction.
Yes. Actually, the intention of this paper some is which that somehow some of the results which are from some earlier time get forgotten. And actually, here is a question: collision of electrons with a metastable nitrogen molecule. So that was a process which was measured in '73, and later we can go to the next slide. And then later by the Paris group, it was studied quite intensively in 80s, so that this process to be very interesting because it had some structure which was characteristic of the so-called boomerang resonance processes, in which the lifetime of the resonance, it means the complex of electron molecule which is created, the negative temporary ion, has a lifetime which is characteristic of the nuclear vibrations. So this is about 10 to minus 14 seconds. So these characteristics was observed in this nitrogen case. And actually in 80s, it was repeated, the experimental investigation of this process, and later also the theoretical study of this process was performed by the local complex potential method, and the rather good agreements was obtained for such a resonant process. Later on, next slide, please. Next slide. Can we go to next slide? Okay, and next one, so that I get my 3 minutes only. Okay, the next slide. okay, it was this local complex potential model which was used for many years, which was developed by late Professor Florence Fayard. She developed a numerical program for this, which we were using many years later on for different cases. And the group of Bari is using it very, very regularly recently for their some studies. And it was used later in 85 for a process which is the key process which we are talking today, is that if we have a metastable molecule, nitrogen, which is somehow very important, state of nitrogen is a long controversy, and many of processes are explained by existence of these metastable states in nitrogen. And actually, the idea of this study was that if we have electron scattering on metastable, then we should have big cross sections for this, and that is really what was somehow by this local complex potential measurement was shown. And later, somehow, the idea of the present presentation was to go through the literature, which is now modern, and to see whether there is some trace of this process actually in the literature later on. And we can go further.
Mm-hmm. Okay. This is current status.
Yes, it was also observed in 89 by Mike Allen and so on. But there's no evidence of such resonance in the theoretical calculation of the electron molecules excitation of the triplet states, what would be expected. And also in the most detailed currently used data set of Itakawa 2006, which are currently used for the modeling. Actually, there is no mention almost of this process. So that we want, on the next slide is shown the experimental cross sections for excitation of V equals 6 of A state by this resonance, and Itikawa, recommended data of Itikawa do not show any kind of the trace of this thing. So that actually it is a question of interpretation of the data and summing of this data. And actually we want to stimulate some kind of the further experiments on this subject, and also experimental and also the theoretical work on this, so that it is the intention of this work. Somehow we didn't want just because there are no new experimental conditions and no experimental data, so we could do some of these local complex potential calculations, but we skipped for the moment, and we are maybe do this in okay, that's about it's this process which is somehow missed, and it might be very important for production of superelastic electrons, which might be very energetic and may influence the breakdown in the air. And also it's also important for the surface reaction of metastable on the surfaces of metal surfaces. So that such a resonance is very crucial to figure out where it is and what is the importance. Okay, that's all.
Okay, thank you.
It took more time.
Okay. No. Thank you very much. It was just fine. Okay, I will stop sharing now. So maybe I shouldn't have stopped sharing because there were maybe some questions. Can you turn off the video in your, because it's on, so it's interrupting a bit with the connection. You have a second button so that you can turn off the video first. Professor Dr. Chadic. Yes. Okay. Thank you very much. So, are there any questions? Any raised hands? Okay, I don't see any. It's
no questions so far.
Okay. To my knowledge, it's a very important subject because of the, for instance, in low temperature plasma, because we all know that nitrogen is very important for the breakdown processes, and it can even take over the breakdown process if it's introduced even in the small amount in the gas. So I see the importance of this of your investigations. So if there are no questions, please ask some questions. Don't be shy. You have several options. You can raise your hand, or you can write to the host, or anyone. Just write in the chat, and we will see it. So thank you again, Dr. Padev, for this interesting lecture. I would like now to call on anyone else who wants to give us his short presentation. We have time, obviously, for this. Please raise your hand or write in the chat. As you can see, it's a very efficient way of exchanging or showing your results. So, host, do you see anything? I don't. Nothing.
I don't see as well, so we can go maybe through the list or something.
Okay. So we will now call out poster by poster, and we will open it and share the files. So you will be doing this. Okay.
The host, the second moderator will do it.
Okay, so we are starting with Natalia Tanska, a DFT study of dissociative electron attachment to, it's some complicated molecule with carbon C5X-H4N and other also C4X-H3N2 are aromatic molecules. Both are hydrocarbons, aromatic molecules interacting with. This is the title of this poster. So Natalia Tanska is with us here. She is present. Would you like to say a few words? If not a short lecture, maybe something? Can you raise your hand if you want to, or we can just wait for questions?
Actually, I'm not prepared to do the presentation. I can tell you that it's just...
Okay, so are there any...
those are simple molecules, pyridine and pyrazine, and substituted with chlorine or bromine. And I did some simple calculations with density functional theory to obtain vertical electron affinities and potential energy curve. To see if this method is capable of modeling the result of the associated electron attachment. So, are there any questions?
Okay. Are there any questions?
No questions so far.
People are holding out. It's almost like there's a problem here with the connection. So no raised hands. Host, can you hear me? Is there a problem with my voice? Can you hear me?
I hear you. I hear you very well. There is no hands, no feedback.
Okay. So if you want, you can talk some more, explain a bit more about this. I'm sorry to say I cannot ask any questions like this because it's not my field.
That's all right. It's actually a very simple method and probably not totally correct because it's a dynamical system, so it should be modeled with Hartree-Fock or density functional theory. but it turned out in the past that this method can give quite good results in predicting vertical electron affinities, and those results are in good agreement with experiment of Lenner and Schultz. And the potential energy curves are quite interesting because during the along the bond of carbon and halogen, there is a symmetry change to go through the P state to sigma state. And it has also been confirmed experimentally, so it's quite interesting that we can obtain the results with the body method.
Okay, thank you very much. Is this of some importance for the simulations of plasma?
Sorry, can you repeat?
Is this of some importance for the simulation of actual low temperature plasma, for instance? These processes are important, yes?
It can be important in astrophysics to see how astrochemistry actually, to see how the ionized molecules are created, for example, and in medicine.
Yes, of course, for plasma medicines, since they are hydrocarbons and so on. So thank you very much for this presentation of your poster.
Thank you very much.
Again, are there any questions other than mine? Okay. We can go now to the second poster. If there is someone, Professor Poparic or Vojnovic, I think they were there at the last lecture, but now I can't see them.
I see Mirjana Vojnovic, but I cannot connect her.
Yes, she's here. Are there any questions about this excitation of the 001 mode of CO2 in microwave E field and DC B field?
No questions so far.
No questions. So, Marina, would you like to say something? Or can we even connect to her, or she's just listening?
No, we cannot connect to her because she's probably from some okay, maybe now, yes.
Maybe from mobile device or something.
Okay, maybe yes. Now we can hear her.
Okay.
Mirjana, do you hear us? Mirjana, do you hear us?
Mirjana, can you respond?
She's unmuted, but
Yes, she is unmuted, yes. There is some problem. Maybe people didn't expect this, but of course, they should have been for the questions. Okay, we will go on then, just not to waste time, and maybe later we can, if there aren't any questions anyway, maybe later we can go back to Mirjana if we have time. So we are going to the poster 3. Yes, it's the same group of people under Professor Poparic. So if we don't have Mirjana, do we have Stankovic maybe here?
no, Violeta Stankovic, she was there, but she left the session.
Just when she was supposed to be there. Okay. So maybe they will be back also.
Yes.
Oh, we're going to the 4. I think at 4 I didn't find people last time I looked. I don't know how it's pronounced, but probably Zivitska and Mozejko, Pavel. and Božena Živička. Are you here? Can you raise your hand, maybe? And I can't find them in the list.
I have found Pavel Mojejko. Pavel, do you hear us?
Yeah, I do. And you?
We hear you now. Yes, that's nice. So your poster is cross-sections calculations for electron scattering from rhodanine and cyanuric acid. Sorry for reading like this. I'm not in the field.
It's
so
okay.
can you tell us something about
It's perfect. Sure, it's a simple work. we performed some simple calculations of ionization cross-section and elastic cross-section for electron scattering. In principle, I'm working in electron scattering with molecules, and we are mostly interested in total cross-section measurements, but not for the targets yet. So, but we also perform some simple calculation. And if you could change for the next slide, maybe not introduction, these two compounds, they are important because they are some promoting compounds which can be used in dye-sensitized solar cells. And of course, in such an environment, most important is dissociative electron attachment process. But we are not studying here this particular process. Could you please change for the next slide? Maybe not introduction. Okay. So here we have a structure of the two targets. Both of them contains C3H3NO, and one of them with two sulfur atoms and one with the NO2 group. So it seems that for intermediate electron scattering, the cross section should be similar and mostly depend on the size of the molecule. And could you change for the next one? Okay, thank you. So we performed the calculation of ionization cross-section within the binary counter beta method. It's a kind of the connection of binary electron scattering from the target, and of course some beta theory for the intermediate electron scattering. And it's a model, not exactly theory, but what is important, all quantities which are necessary to calculate can be obtained just using some quantum chemical codes. So there is no free parameters in that model. So it's not a question of scaling or something like that. And for the single ionization cross-section, this method is quite good. On the next slide, we have some information about if you could change for the next one.
The next slide, yes.
Okay, the slide, okay. So the quality of the ionization cross-section is, I think, within plus minus 15% in comparison with experiment. Okay, it's not, there is no experimental data. We are using this dot line plot just to see our just to show our cross-section, calculated cross-section, and of course, even in ionization process, the efficiency is higher with the compounds which contains sulfur atoms. And on the next slide, we have a comparison of ionization and elastic scattering with the cyanoacid molecule. Here, elastic cross-section, of course, we have used very simple independent atom method with polarization and static potential. And of course, I think that cross-sections are quite reliable for the intermediate energies, because the assumption of the method is that each atom scatters independently. So we have molecules, in fact. so it can be reliable for the higher energy. And of course, it's a kind of the work in progress. We'll calculate more, and I think that's it for this short presentation. If you have any questions, I will try to answer.
Okay, thank you very much. This was also a short and concise presentation. Do we have any questions in the chat? I don't see any. Do we have some raised hands?
Yes, we have one raised hand.
Istok Chadej, okay.
Yes.
Yes. Feel free to ask your question.
Yes, do you hear me?
Yeah.
Okay.
Yes.
I would like to ask you, what is your ionization cross-section? Is it just a single ionization cross-section, or it's also the multiple ionization included in this model, and some kind of dissociations also occur, so that what is precisely the ionization cross-section which you model?
Okay. Thank you. Exactly, it's a single ionization cross-section. In this method, it's assumed that we calculate ionization of each electron in the molecule. Okay, so just and the total cross-section is the sum of ionization efficiency of each molecular orbital, but it's a single. There is no multiple ionization. Okay, so in fact, it's when I compare, for example, for simple molecules like SEF4, for example, silicon tetrafluoride molecule, it will be lower about, I think, 10% from the total, okay, including all other processes.
Okay, thank you.
You're welcome.
Okay, thank you, Dr. Chadej, for your questions. I would again like to ask all the attendees to show some initiative and feel free to ask the questions. So thank you, Pavel, for your lecture. We will be now going further on to other posters. This was number 4. Now we don't have number 5. It's not. It was not in the virtual poster gallery, but we have now a gap in our in the presence of our poster contributors. So I would like to call anyone that it is between 6, 8, and 9. 8 we have already done. So 6, 9, and 10. Bunjac, Milošević.
6 we done as well. So 7,
yes,
9,
6 we have also done as well. So I have just seen it. So Bunjac, Milošević, 9 and 10. 5 we don't have. 8 we have done. So is Milošević and Bunjac, are they here? I don't see them. Okay, we can go
not
on.
in the session. Yeah, go on.
Okay. So 11 is Delibašić and 12 is, I think this is Igor Savić, yes? Do we have them here? Yeah, Igor Savić is here, he raised his hand, and Nenad Simonović raised his hand. This is for the 10. Simonović is for the 10 and 9.
Okay. So
Hello.
Ja ne znam šta Nenad Simonović šta hoće da kaže. Ovdje hoće za 10 pitanje. On je nešto rekao kao i 9 i 10.
So we will first talk to Nenad Simonović. 9 and 10, yes?
Yes.
So you will present 9 and 10, yes?
Yes.
Okay, and then we will go to Savić, who is also obviously. So please feel free to present. Would you like to present, to say for it?
Very briefly, a few sentences.
Okay,
because you started. Yeah, okay, so we have 2 posters. I'm the 4th at the end of, okay, so you can see. Okay, so this poster is devoted to hyperfine splitting. So of the lowest state positronium in strong electric field. So it is known that positronium is an unstable system because it consists of one electron, one positron, so they can annihilate. So this is one kind of instability. Another kind, if you put this system in an electric field, then this system becomes unstable because of possibility for field ionization. So it is completely, so it's not annihilation, but simply electron and positron can separate, and again positronium is destroyed. So these two kind of instabilities are studied here, and it is found that for weak fields, annihilation is a more dominant process, but for stronger fields, field ionization dominates. So there is possibility that positronium is will be faster destroyed by the field. So positron electron will separate before they have opportunity to annihilate. So that's the point of this poster, and I will not talk more about this, so I can finish. So I don't know, can I say a few sentences on next one, or just see if there are some?
We can go. Would you like first to see if there are any questions for the 9 and then continue to 10, or would you like them to?
Maybe just to check if there are some questions. If not, then we can go
No
to
questions.
Okay, no questions so far. Again, just to ask, are there any questions about poster 9, hyperfine splitting? No, so we can continue now to the poster 10.
Okay, so this is another system. This is sodium, which is irradiated by femtosecond laser pulse. And there is also field ionization, but not in a constant field. Okay, you can stop to see figure 1. It's important. So figure 1 shows 4-photon absorption, which leads to ionization of a sodium atom. So you see it starts from the ground, 3s state, and absorbs 1, 2, 3, these arrows. Each arrow is one absorbed photon. And the 4-photon simply gives energy of valence electron in sodium to leave the atom, and you have practically so-called 4-photon ionization of sodium. And that's the point of this paper. We simply consider the spectrum and compare with the experiment. On the figure 2 right column, you see comparison with numerical calculations and experiment. Experiment is black line and numerical calculations green line. So you see that the main peaks, simply comparison between the theory experiment is quite good. So that's it. So if there are some questions, I can give answer.
Okay.
If not,
Thank you very much.
Continue. Yeah, welcome.
No questions so far.
Okay, thank you.
Thank you, Professor Simonic. It was very nice.
Okay,
so bye. We will now continue with the numbers 11 and for the 11. Did we have Professor Manchev maybe, or Delibasic, Milojevic?
We have Delibasic. He is on.
Okay. It is Danilo Delibasic. Okay. Single electron capture in pH plus collision. It's proton H plus collision. Would you like to say a few words? Though I think the connection is bad or something is wrong with your microphone. I can hear you very weak. Can you say something for the test's sake? Can you hear us?
Another microscopic test.
Can you hear us? His microphone is off now.
Maybe two more.
Yes, maybe. So.
Hello.
Is this Danilo? Yes, you can hear us.
Yes, this is Danilo.
Okay, can you? We have just wasted a bit of time. Can you, in a few minutes, do you want to, in a few minutes, say something about your poster?
Well, yes. Okay. So we discussed collisions between ions, between protons and helium ions, where the helium ion has one electron. We treated this collision in the framework of the high energy CB13B theory, which satisfies the correct boundary conditions in both the entrance and exit channels. And we contrasted our theoretical results with the experimental data and found very satisfactory agreement. The theory is not new, but it wasn't applied to the collisional system in question. So that is we were the first who applied it to this concrete collisional system. And as I said, as we can see, the results are in satisfactory agreement with the experimental results. Even better agreement is expected at higher energy values, since this is a high energy theory and the available experimental data is maybe in the intermediate energy region. And that is a concise explanation.
Okay, thank you very much. I see these energies are rather high for me. For my plasma, it's 30 kilo electron volts where you start. Yeah, it's very high.
Yeah.
Yes,
So it's around around 20 kilo electron volts are about low energies for this kind of theory. It is expected to work for higher energies than about 20 kilo electron volts.
And what happens with the cross sections when you lower the energy, regardless of the theory? What do you expect if the energy is lower, for instance, 5?
In this collisional system, there are available experimental data for lower energies, but the agreement is it gets worse.
Yeah, yes, but what happens with the cross section in the experiment? Does it go much lower, or does it come horizontal? Does the value is constant also?
So regarding the experimental cross sections, right?
Yes. What happens if you roll?
They go a bit lower, not drastically, but they do go a bit lower.
So these kind of collisions can occur also at lower energies, not only at high energies.
I can't understand.
These kind of collisions with these products can also occur at lower energies. It happens.
They can.
It's like improbable. But the theory is valid for high energies. Okay.
Yes.
So thank you very much. Are there any questions?
No questions.
No questions. Thank you, host. So we go to the Igor Savic now to poster number 12.
So, Nicola, did you hear me?
Yes, I can hear you.
Okay.
It's just fine.
Good. I will just say a few words about a new instrument that we have in my city at my university. This is a new guided ion beam instrument dedicated to measure absolute integral cross sections for collisions between neutrals and ions. So, a couple of years ago, with my colleagues Stefan Schlemmer and Dieter Gerle from Germany, we started to build this instrument in Cologne. And 2 years ago, this instrument have shifted to Novi Sad and now is operational completely. Could you just jump to another slide, please? So, purpose of this building of this machine was to understand elementary processes occurring in any kind of technical or astrophysical low temperature plasmas. Next slide, please. Basically, this instrument consists of the storage ion source. When you introduce the gas, you ionize the gas by electron bombardment. You can store these ions. You form a really zoo of any kind of ions. You can store them for a certain time. You can add a buffer gas. You can a mixture of gases, and then you eject these ions into the first quadrupole to select primary ions. Then these ions are injected to the octupole as an ion guide, and these ions are flying to the scattering cell. In the scattering cell, occurring the collisions between ions and neutrals, okay, and products and primary ions are then ejected to the second quadrupole, mass analyzed, and then detected by daily detector and counted. So basically, we can do any experiments with any ions and any neutrals, okay, in order to study or let's say to measure absolute intercession. Next slide, please. So this is the picture of this, let's say, simple or complicated machine. Next slide, please. Basically, all these techniques are based on guiding the ions using inhomogeneous electric radio frequency fields. Okay, next slide, please. Next slide, please. So one of the first results or first systems that we have studied was the collisions between H2 plus and H2 forming H3 plus H. That was really a challenge since in the literature we have seen that above 2 electron volts was steep decline of collision, let's say, cross sections, and already at 10 electron volts in the center of mass system are the, let's say, 2 order of magnitude lower that we measure. We compared our results with existing literature data, and we found out that we are in excellent agreement with other guiding ion beam results from the group of Czech-Ung, but all other, let's say, much older results showed steep decline. So we measure this reaction again, and we propose new, let's say, analytical function for this reaction. This is really the shortest resume what I can say.
Okay, Professor Savic.
Of course, please, I just have to mention that nothing of this would be possible without financial help of Deutsche Forschungsgemeinschaft.
Okay, Professor Savic, thank you very much. It was an interesting to know that we have such a device here. I'm especially interested in this kind of collisions because I was doing some Monte Carlo simulations. So I don't want to burden now the audience with my questions. I will probably have some questions for you about these proton transfers that we're creating. H3 plus is very important for hydrogen plasma.
Yes,
because it becomes the dominant ion very easily. Are there any questions from the audience?
No questions from the audience.
No. Okay. Thank you again, Professor Savic. So we can go on. We are looking at number 13. I think we have no one from this. Is Raspopovic here or Nikitovic? Željka Nikitovic? No.
No, they're not on the list of participants.
Okay, we have done 14. We are going now to 15. We have done. And we are going to Duško Borka, number 16. Channeling potential through radial deformed triple wall carbon nanotubes.
Oh, okay. Do you hear me?
Yes, yes, we can
Okay,
hear you.
I will very briefly present this poster. In this poster, we presented a theoretical investigation of channeling interaction potential between proton and radially deformed triple wall carbon nanotubes. Why we choose triple wall? There are a lot of theoretical groups. They are working in ion channeling investigation, but experiments are still in the very beginning. The most challenging task in experiment is to solve the problem of ordering, tightening, and holding nanotubes. And there, I know for 2 experimental evidence of ion channeling through carbon nanotubes, and both of these experiments are performed with multi-wall nanotubes. We take triple wall because it is a 3-layer, 3-wall nanotube, because it is easier to make a simulation where with 3 than with 10 wall of nanotubes. It is a reason why we take triple wall nanotube. And in reality, if we apply some mechanical stress on carbon nanotube, radial deformation can appear. Also, carbon nanotube can be radially deformed if we apply external electric field, or that is why it is important to investigate radial deformation, because it is a real effect. And our theoretical model that we use assume continuum model approximation. We calculate proton nanotube interaction potential as a function of proton atom distance, and we use Molière approximation of the Thomas Fermi interaction potential. We presented in this poster 4 cases when nanotube is perfect, and when radial deformation is 0.1, 0.2, and 0.3, and radial deformation is characterized by the dimensionless parameter eta, and you can see the formula which says that eta can be expressed like if we divide r minus r y and divided by r, where r y is the semi-major axis and r is the radius of the 4 nanotube. And at the end, we obtain this formula for interaction potential. And why it is important to us, we can then calculate spatial and angular distribution of channeled ions through these deformed nanotubes, and also we can investigate channeling properties of this kind of system. And if there are some, this is a very short what we presented on poster, and if you have some questions, please.
Okay, thank you, Dr. Borka, for this lecture. It was like a short lecture. For
No
me,
questions from the audience.
no questions from the audience at this moment. I'm afraid I cannot ask any questions because this is very space physics to me. This is when it's the carbon nanotubes and so on, or any nanotubes. So thank you very much.
Okay.
So we will continue now. Okay. We have been. Sorry. Is there anybody?
Miss Christina Delibasic is online.
Okay, we are going to Christina Delibasic now.
Oh.
It's number
22.
22. Yes, 22.
22. Yeah.
You are coming for Kragujevac, yes?
Yes.
Yes, from Serbia. Numerical investigation of the plasma formation in skin tissue. You are having some problems with the microphone. If there's some kind of echo, maybe you can put the volume down.
I don't know what can happen, but can you hear me now?
Oh, now it's fine.
Okay.
I will mute myself.
Okay, thank you. I would like to say that I haven't prepared a detailed presentation, but I will be more than happy to answer any questions you may have or to say a few sentences related to our paper and the collaboration. I would like to say that our colleagues from Spain are currently working on the optimization of skin artificial models by including cells from the immune system to achieve more realistic skin equivalents useful for drug delivery, cosmetical testing, and medical applications. To achieve this, it is important to know how laser affects different layers of skin and calculate important parameters such as free electron density and free electron temperature. Because of that, we are now working on developing an exact theoretical and numerical model. The final goal of our group is to compare experimental results with our theoretical and numerical approach. In this paper or on this poster presentation, we showed in figure 2 and also in figure 3 evolution of free electron density for different gain and loss processes for different wavelengths. I would like to say that we compared also analytical solution of equation 1 with our numerical simulations, and we are getting really good results. That is all from my side.
Sorry, I have to unmute my microphone. Thank you, Christina. Thank you very much for this lecture. It was the images are very nice and it's a very applicable and contemporary subject because of all the interactions of plasma with skin and biomedicine. So, are there any?
Sorry.
Say yes.
We started to work on this model just a few months ago. And this is our first paper to be published, potentially published. So we are looking forward to I don't know, to describe all theoretical models related to this phenomena.
There are a lot actually, yes, because as you said, there's a Bremsstrahlung and also radiation and all kinds of things. Yeah.
Yes.
No, it's not easy, but it's better to have some first approximation than nothing.
Yeah.
And of course, are there any questions here? This would be a good place to find some ideas or advices. So we have no questions, but also feel free to find the email in the book of contributing papers of our authors, and then you can also ask questions via email if you are not ready now to ask. So I would like to thank Christina Delibasic again.
Thank you very much.
Okay, thank you for presenting. We are going now to number. What was the number that we already?
24 is Biljana Stanko. She is ready for presenting.
Yes. appearance of B2436 line with forbidden components in LIPS plasma. Okay.
Yes, hello.
Hello, we can hear you. You can start.
Hello. So this is a LIPS experiment on beryllium oxide target in low pressure gas mixture. We did this in order to see if we can get beryllium spectra and record beryllium spectra. Previously, we did a similar experiment on beryllium, but in pulse discharge plasma. So this is LIPS for like comparison. On the left side, you can see the experimental setup on the left side of the poster. So, of course, first thing that we do is diagnostic of plasma parameters. So we calculated the electron density and temperature, which you can see in graphic in the right side. And if you can go a little bit low, I want to show a picture, of course, so the results. This is the evolution of beryllium line. So on the blue wing, you see additional component, which is forbidden component of beryllium plasma. That component we recorded for the first time in the pulse discharge, and now we see it again in LIPS plasma. So we measured the wavelength peak separation and peak intensity ratio for the pulse discharge plasma, and you can see that picture on the right side. And also by that figure is the wavelength peak separation and peak intensity ratio for the LIPS experiment. So this experiment is in first phase. Firstly, what is important is that we recorded the beryllium lines and beryllium lines with forbidden component. So the next step is, of course, if you can go a little bit lower. So the next step is, of course, to do correction for self-absorption, to use specially resolved measurements of beryllium and hydrogen lines, of course. So that will be like our second phase of experiment. So that will be that in short. Thank you.
Okay. Thank you very much. Do we have any questions?
No questions so far.
Okay. So you are planning on, if I understand correctly, you are planning on using beryllium line, and you have now compared it with the standard method of H alpha to calculate electron density, yes?
Yeah, we use the H alpha for electron density, yes. And what we actually want to do is to compare the beryllium lines in LIPS experiment with those in pulse discharge. In pulse discharge, we had a problem with a large amount of beryllium dust, which is, of course, toxic. And we have a situation that we had really wide beryllium lines. So we want to see what will happen now in LIPS experiment. And also to do comparison to a theory and so on.
And so when you compare these two, they are in the LIPS experiment, how they compare to, how does the line shape compare to pulse plasma? Is it also very wide or?
No, it's not that wide.
It's not the same, okay.
It's not the same.
And why do you have to use ionic beryllium line? Is it because the plasma is ionized so much, or why is it not, my simple question is, why is it not neutral? Why is it not neutral?
Because this line with forbidden component, we are the first people to record it in pulse discharge. So it was like nobody knows about existence of that line. So we want to also record it in this LIPS experiment. That's the main reason why this poster is about that line. And we want to use hydrogen lines so we can have, so we don't have to use beryllium lines, so we can have separate methods.
Yes, you need to use hydrogen like a standard method, like a standard.
Yes, that's why.
But it's interesting that there is this the forbidden component of this beryllium line appears. I have also been. I'm familiar with the work of Professor Ivkovic, and I know of his previous work with forbidden lines. So it's very interesting. Yes. How did you know that this beryllium line would have this? Did you just notice it in your spectrum?
We noticed it in our spectra. Yes, we noticed it, and at first we didn't know what it was. We thought that it maybe is line from gas. Mm-hmm. No, from gas, or like from argon, because argon has a lot of lines. But it's not. In the end, it's not from oxygen, and it is actually a beryllium forbidden component. So we got a little bit lucky.
Okay, so since we have this spectroscopy audience of some important names in spectroscopy present, we have some interesting questions.
Yes, of course.
We have from Sili Saha Bresho and Nabil Ben Nesip. So first we can ask Professor Bresho to ask.
Yes. Do you hear me?
Yes.
Yes, we do.
Okay. So my question is about the width of this beryllium-2 line.
Yes.
I think it's due to Stark broadening. I see also that the forbidden component is rather far in the wing. So I hope that the broadening can be evaluated by assuming that the line is isolated in the center and in the width. So there are results that exist for this line. Have you tried to compare your result with the theoretical broadening which exists? You can find it in the studies database.
Oh, you mean theoretical, like yes, we like the beryllium spectral line. Yes, we compare it, but in our pulse discharge experiment, it appeared to be like 3 times wider in experiment than in theory.
I saw that.
Yes.
This is why I asked this question.
Yeah, that is why we do the ellipse plasma experiment.
Okay, thank you.
Among others, yes.
So we can go to Professor Bresho. Do you want to have another question, maybe?
No, that was my question.
Okay, thank you very much. So
thank you too.
Thank you.
We will now ask Professor Nesib for his question. Please.
You hear me?
Yes, we do. Yes.
Okay. So nearly the same question as Sylvie. So there are in Stark B this line and the width of this line calculated by Milan Dimitrievich and Sahil Bresho many years ago, so you can compare. Same question.
Yes.
Same answer. Okay, thank you.
Yes, we did that. But of course, also, I want to say we need to do ellipse experiments so we can do correction to self-absorption also.
Yes.
Because we are not able to do that. So that is another reason that we need this ellipse experiment.
Thank you.
Okay, so are there any other questions for this obviously interesting lecture? The only one with questions so far, almost.
No questions.
The second one. Okay, no further questions.
No questions. Yes? No further
thank
questions.
You, host.
Thank you.
Thank you also. So we will now see if there are, as I was informed, there is no one else present. Maybe Jovica Jovic, is he here? No? Nedic, Vasiljevic.
Yes. Vasiljevic.
Vasiljevic, 28, yes?
Vasiljevic is present, yes, 28.
Okay. Okay, this is from the Faculty of Physics, and we are dealing here with the measurement of
rotational and gas temperature in Grimm glow discharge using Q branches of full alpha band through the cathode sheet region. So we did all the experiments in pure hydrogen. Purity was 99.999%. So first to determine the cathode sheet distance, we use the hydrogen alpha line, and we estimate electric field distribution. So we use the Hadal function. This is the formula 1 and the figure 1 below the formula. So we compared our best fit results with the experimental profile. And here in figure 5a, we can see our distance of the cathode sheet region. And then we use the full hair branches, full hair Q branches, 0, 0, and 1, and 2, 2, to determine rotational temperature. And then also we calculated the population of excited energy levels determined from relative line intensities to derive a rotational temperature, distribution in the cathode sheet together with the relative population densities of the rotational levels, as can be seen in figure 4a and b for gas temperature. And also this results is published in the paper. The paper is published in JQ of SRT this year. And in the paper we presented also Q3 branch. So yeah, that would be it in short.
Okay, thank you very much.
Yeah, if you have any questions, I would be glad to.
Yes, we have some questions.
Okay.
We have a question of argon ion 2. What is the difference between Jones and your calculations from Nabil Nesib? So I will repeat. What is the difference between Jones and your calculation? Is this question for you?
That is not a question.
No, actually, that is the question. He's writing now, sorry. He's writing, this is the question for poster 30.
Yes, poster 30. Yeah.
Okay, okay. I'm sorry, I cannot.
Sorry,
I
didn't write for
cannot
which
give you an
poster, sorry.
answer.
Okay. So
it's
okay,
fine.
we have not yet moved to this poster. Okay. So let me ask you again. I was not very careful. You measured the rotational temperature, and the purpose of this is usually to measure actually the gas temperature or
The
find
gas
some correlation.
temperature.
Yeah.
Yes,
And
yes.
how did you measure this on the graph that says gas temperature? How did you measure this?
So
because you have rotational separately and gas temperature in the graph.
The gas temperature is basically calculated for the ground vibrational state. And it's two times larger than the rotational temperature, according with the relation of the rotational constants for the upper and ground state.
Yes,
and
there are calculations
that can
about
be
this,
seen in the table one, just above figure 4. Okay.
Yes. Okay, because there are always questions what is the relation. I have also measured this and used the evening green discharge, and there are always this question, how is rotational temperature actually correlated to the ground temperature? There are many papers about this. So you are considering this temperature more or less to be the ground vibrational levels to correspond actually to the gas temperature, and and then you compare them to the Kaiwa.
Yes, yes, it's true.
Also, in this group that you're working now, they have also compared it with some thermocoupling measurements and so on. So
yeah.
So thank you very much for your lecture.
Okay, thank you.
So I don't know what should we do with these questions. What do you presume we do with this question 30? We should move to the poster 30 if there are no other. Is anyone else present after? Is 29? We don't have even 29 on the gallery, so we're going to the 30. Is Professor Đurović here or Blagojević? Do we have them?
No, they are not in session.
Yeah, I didn't see them also, but maybe I was thinking there was something wrong with me. So let me see. Yes. So Professor Nesib, I must say you must find another way of asking them. You can use the email, or of course you have contacts with Professor Đurović.
Okay, thank you.
You can write to them, so they will respond if they are not. So we have now finished with calling out poster by poster and all the present participants and contributors. So I would like to ask again, all of you, is there something that some of the presenters would still like to say something that didn't? We have some of them present, but those not to. Or maybe there are some additional questions like the one we had now. So if there are no other questions and no one else wants to present, no one raises their hand.
No one raises
No
hand.
one. Okay. So we have prolonged this session for about 15 minutes. It's not too much, I think. I would like to thank all of you for being present here and giving your contributions and asking questions. This form of communications can be very interesting. As you can see, it could be very nice way of sharing ideas. So I think we have used this potential to some extent. So maybe the day after tomorrow, I'm calling you to go to the second to be present at the second poster session. I will also be chairing this session. So we will be again. Am I right? It is on Thursday. Yes, Thursday evening at the same time.